All right, great. Welcome, everyone, and thanks for taking some time today to join us for this webinar on disaster recovery options with AWS. My name is Robbie Wright. I lead product marketing for Amazon S3 and Amazon Glacier. And joining me today is Brad Dispenza, an AWS solution architect, who will be walking us through some demos of the different DR scenarios on AWS. And we've got quite a bit of content to cover in a short time today, so let's just go ahead and jump right in. Disaster recovery is a hot topic today for a number of reasons. First, many of you are telling us that you're starting to feel squeezed by the shrinking SLAs that your businesses require for the applications that are running in your on-prem data centers. And we live in a world where really every application is considered mission critical by someone in your organization. So often those SLAs mean that you need to put a DR plan in place for a workload that's never had it before. And then second, if you still have a lot of infrastructure on premises, cloud is becoming the preferred infrastructure choice for disaster recovery because of the economics, making it possible for you to bring DR to more applications. But solutions could look really different depending on your needs. So let's spend some time walking through how you can define those needs. The first phase of discovery is pretty straightforward. You need to identify the applications that you want to protect and define what protection looks like for them. It's helpful to do a business impact analysis to determine what disaster recovery is really worth to your business and to give you an idea of the cost targets that you want to work within. Based on that, you should set recovery point and recovery time objectives. Let's spend a minute talking about RPO and RTO. A recovery point is the maximum acceptable data loss for an application. So if we plot it on our timeline here, the recovery point is sometime before our disaster occurs. Our expectation when we set a recovery point objective is that all data up to that point will be recoverable in the event of a disaster. Looking at it another way, if a disaster strikes, we can expect that we will lose the data between our recovery point and the time of our disaster. You'll find RTO, or recovery time objective, after the disaster on that timeline. Your recovery time objective defines the amount of downtime you're willing to accept for an application. And this tells you how quickly you need to be able to have the application back online. It probably goes without saying that as your RTOs and your RPOs grow smaller, they can become more complex and more costly. So it's important to pair your applications with the right type of recovery. Applications can be placed on a spectrum of complexity. Business continuity ensures that critical business functions continue to operate or recover quickly despite serious disasters. Disaster recovery, or DR, is how you get there. DR enables the recovery or continuation of tech infrastructure and systems following a disaster. So based on your business impact analysis, you should be able to define RTO and RPO for an application and fit a DR solution to those objectives. At AWS, we talk about 4 general levels of DR support across this spectrum of complexity and time. For our less valued use cases where RTO and RPO are hours, it could be as simple as using your backup software to write a copy of your backup data to an AWS storage gateway or directly into Amazon S3. And this is what many of us are used to in enterprise environments for our hundreds or thousands even of long tail applications. We've probably also got use cases that are a little more important, but their business value might not warrant a big infrastructure investment for DR. Let's say we attach an RTO and RPO of anywhere between 15 to 60 minutes to those applications. And for most of us operating in our on-prem data centers, these were the applications that were most at risk because there really wasn't a DR infrastructure that fit them well. So our DR plan, if you can call it that, was really to just hope and pray that nothing ever went wrong, and then have an updated resume ready for whenever it did. Not really the scenario that any of us want to be in. But today there's really a solution. We call this a pilot light scenario, where we have resources ready to go in AWS, but we don't light them up until we actually need them. Now, for business critical services that require RTO and RPO in minutes or even require near zero downtime, you should consider either warm or hot standby, and potentially even consider multi-site deployments. These types of solutions typically include advanced orchestration of your DR runbooks. But here's the good news. DR is no longer an all or nothing thing. Choose what applications need to fail over and what applications don't. Some applications are more important than others, and DR doesn't have to be that one-size-fits-all solution anymore. So let's spend a few minutes unpacking these scenarios. First, AWS has a large ecosystem of partners that complement our services. You can see a high-level list of our storage and ingest-related partners in this slide. I'd like to focus on a few select partners that provide compelling solutions to replace traditional backup, recovery, and archive environments and provide ease of use, lower costs, and scalability by leveraging S3 Standard, S3 Infrequent Access, and Glacier storage classes as cloud storage targets. Let's look at backup and recovery. This simple and low-cost DR approach backs up your data and applications from anywhere to the AWS cloud, and that makes it available for use during recovery from a disaster. Unlike conventional backup methods, data is not backed up to tape. Amazon EC2 computing instances are only used as needed for testing. And then with Amazon S3, storage costs are as low as 1.5 cents per gig stored for infrequent access. So with backup and recovery, you can assume an RPO and RTO of sometime less than 24 hours typically. As far as AWS services that you'd use for this scenario, Amazon S3 is used to store data with 11 nines of durability for the objects that are stored there. And then transferring data to and from S3 is typically done via the network, and it's accessible from any location. If your backup vendor isn't natively integrated with S3, you can use the AWS Storage Gateway to move that data into S3, and I'll talk more about that in just a minute. Other customers also use AWS Snowball to handle that initial load of large data sets into by leveraging hardware arrays that we ship you, and you can ship data to us basically in 80 to 100 terabyte increments and securely transfer that data into AWS. EC2 is used to set up the computing instances that replace the failed infrastructure, and Route 53 switches DNS records to point to the new structure in AWS. As I mentioned before, the AWS Storage Gateway gives you several options to help you get your backup data into the cloud. The File Gateway enables you to store and retrieve objects in Amazon S3 using industry standard file protocols. Files are stored as objects in your S3 buckets, which are accessed by your backup software through an NFS mount point. The Volume Gateway presents an iSCSI target to provide a block storage interface if that's what your application requires. The Tape Gateway presents the storage gateway to your existing backup application as an industry standard iSCSI-based virtual tape library, or VTL. And that consists of a virtual media changer and virtual tape drives. So you can continue using your existing backup applications and workflows while writing to a nearly limitless collection of virtual tapes. Each virtual tape is stored in Amazon S3, and then when you no longer require immediate or frequent access to data contained in a virtual tape, you can have your backup application archive it from the virtual tape library into Amazon Glacier, even further reducing storage costs. AWS customers do some very creative things and routinely come up with solutions that we haven't even thought of. We have a customer based on the East Coast of the United States that needed to retire some aging network attached storage infrastructure, and those NAS devices were being used for file services for end users with Windows and Mac clients. One of the requirements was for full SMB support. This means SMB v3 with Active Directory, SMB signing, header and payload compression and encryption, and all the goodness of the Microsoft implementation. There was also a requirement for high availability and failover. To achieve those two requirements, the customer deployed 2 storage gateways in volume mode, each connected to a Windows server via iSCSI. And to achieve HA, they were using Microsoft DFS to present single share to end users, and that data is stored on both Windows servers. Any component for a Windows server can fail, and the recovery is measured in milliseconds. This provides highly available local file services with 2 durable copies of the data stored in S3 by the Storage Gateway service. The cost for 2 copies of the data in S3 is 4.2 cents per gig. That's significantly less than storing redundant copies of data on premises. For the DR site, Microsoft DFS replication, or DFSR, is used to replicate the data to a Windows server running in EC2 in US West 1. This provides a DR copy that's geographically isolated from the primary data set. The DR copy can be used for file services in the event of a disaster when both on-premises servers are not available. For added data protection, snapshots are taken of a volume in US East 1. Now let's look at the Pilot Lite scenario. Pilot Lite DR architecture is great for meeting those longer RTO and RPO requirements. In a Pilot Lite scenario, we have resources that are built around a replicated data set. This basically leaves these resources staged in a stop state to respond to a disaster scenario. Then when events dictate, we start up this pool of resources, use auto-scaling to match the required production capacity, and then cut over the system to AWS in production. So in this case, we see a presentation of our corporate network, and then the same resources pre-configured in AWS that we were running on-prem, but these are in a stop state. The only thing we've got in our data volume for our database, and we're just streaming data constantly into it. So then when an event occurs, we can just cut over our DNS record, take those instances. They start up in a few minutes, depending on the load that you have on those resources, and then you're up and running in AWS. And this is good for small scale workloads. And now Brad will show us a demo of what a Pilot Lite scenario looks like. Take it away, Brad.
Thanks, Robbie. So what I'm going to show you all is a quick actual demonstration of the Pilot Lite scenario that we just outlined. However, in this scenario, instead of using a corporate on-prem data center, we're going to fail over from one AWS region to another. So what I want to show you first is how we're actually going to do this. So we're going to start off here in the Route 53 console, and you can see that I've created a pair of hosted zones in Route 53. And this one we're going to use Pilot Lite. So we have a Pilot Lite that has been configured for a routing policy with failover, and we've also configured a primary and a secondary for our failover environment. The way that the health check is going to work is, if we look at the health checks for Route 53, we've configured a specific health check for the Pilot Lite scenario. Looking at our Pilot Lite configuration, we can see that we have an environment that is currently healthy. And what the Pilot Lite health check will do is check the status of a known target, in this case, a URL, and then verify the health of that target. So let's look at what's happening behind the scenes. First, in US East 1, you can see that we have a healthy EC2 instance with Pilot Lite demo. Likewise, in the West Coast, we have another Pilot Lite demo that has been configured identically to the first server. However, notice that as this is a Pilot Lite scenario, the instance is configured as stopped. Inside the Route 53 health check, we've configured an SNS topic that will be used in a trigger for Lambda. Inside the Lambda console, we can see that we've configured a Lambda function to listen to this SNS topic. And we can see that the Lambda code is fairly simple. In this case, all we're telling Lambda to do is when the SNS topic is triggered, start the particular instance. So on my side, if we look at the actual window right now, we can see that we have our target website with US East demo website. Behind the scenes, I'm going to log into the server and stop the Nginx environment. Now notice we have our server now offline, and we can see that the remote host is no longer responding. Let's go back to the EC2 instance in Oregon. And here we can see the EC2 instance has now started to come online. As we said, for RTO and RPO purposes, this instance will take approximately a minute to come online. Once the instance has fully initialized and gone online, just like the prior instance, you'll see that the Nginx web server will come online, and when we reload our web server web portal page, we'll see a similar message to the prior, only in this case, it will now tell us that we are on the West region. And here we can see we've now failed over to the US West 2 region, whereas before we saw US East 1. Again, this was configured via the hosted zones and the failover of the secondary record. So here we can see the secondary record that we've failed over to. And that's a Pilot Lite configuration for DR failover. Back to you, Robbie.
Perfect. So the next example is what we'll call warm site or warm failover. So warm standby is great for solutions that require RTO and RPO in minutes. This is a slightly higher cost DR option that's good for core business critical functions that don't necessarily need full hot site failover. So it's a similar topology to Pilot Lite, but now we've got those resources that are available, and they're there, but they're smaller. Maybe we don't have as many of them, so we just have the bare bones of what we need to be able to come back online quickly. So that when we have that failover, those resources are there. We can use something like auto-scaling to add more to the fleet as we start to take those loads off the primary network, and then we're back online. And of course, the other classic example is a hot site. This is the most expensive example of what you could design for disaster recovery outside of a cloud environment. This is a complete one-for-one matchup of everything you have. So I want to, in real time, be able to take my resources and fail over to a complete clone. Again, really, really expensive, but that's because everything is there and available all the time. I'm running 2 of everything, and it's in a physical world. There are some pretty big cost concerns there because you now have to pay not only for those resources, but for a second facility, for separate data lines from a telco provider, and other costs that mount up pretty fast. So in this case, for failover, we just switch our DNS record and we're off to the races. And with that, I'm going to pass it back over to Brad to run a quick demo of what warm and hot site recovery looks like.
Thanks, Robbie. So in this case, I'm going to show you an example of a warm demo, but you can see that the technique that we're going to use for a warm site is going to be very similar to a hot site. We're just going to configure the timing a little bit differently. So just like the Pilot Lite scenario, you'll notice that I've created 2 hosted zones within our record set here. In this case, we're using warm demo. You can see that just as before, we're pointing to a failover with a primary and a secondary. And in this case, we can see that the instance environment also includes health check. So here we'll select and assign the warm demo health check. In this case, what we're going to do is, just like the previous example, I'm going to simulate a failure from, this time, the West Coast to the East Coast. But our environment is a little bit different. Whereas a pilot light scenario had just 2 servers running, in this case, we're assuming that the environment already has some capacity already provisioned. So in this case, we can see our Oregon server environment is already running behind an elastic load balancer. And we can see in the Virginia region, we also have a similar environment. But in this case, for the warm standby, I've pre-configured the auto-scaling group to have only 1 instance running. In this environment, our simulated failover will be that we want to have 2 instances so that we can take double the load. However, because this is a warm standby and not a pilot light, we are running with a minimal amount of capacity. So let's see what happens when we simulate a failure. So what I'll do is, in our Nginx environment that is in Oregon, I'll create a failure in the Nginx environment that will cause Route 53's health check to fire and detect that the environment has failed. Similar to the previous example, I've also configured a Lambda function that will listen to an SNS topic, just like we did for the pilot light environment. However, this time we can see that the Lambda function is still simple, but a little bit different. In this case, you can see that what we're going to be doing is responding by changing the auto-scaling group, in this case, warm demo, to change the desired capacity to 2. When we go back to the service console for the Virginia region, we should see, and there it is. Notice that the environment now has been configured for 2 instances. We've configured our environment to desired of 2 with a minimum of 1 and a maximum of 2. In this case, we want to make sure that we don't add more capacity than what we actually want in order to run our environment. Now, if we go to our warm standby, here you can see in the original environment, I included a lower footer that indicated that this was in the US West 2 environment. If the failover has occurred correctly, when we reload the environment, what we should see is that that footer is removed. And in this case, this environment now is running entirely in the East Coast region. If we wanted to do a hot site failover, we could configure this to be faster by reducing the TTL amount that's caching the warm demo record here in Route 53 to a lower number. But in this case, you can see that the entire environment took only a few seconds to fail over. If we were to do this as a hot site, we could also include services like CloudFormation to add additional capacity as well. But traditionally, in a hot site environment, you're running the exact same stack as you were in the production environment. In a warm stack environment, we also could use that same CloudFormation template to add additional resources, or just as I demonstrated here, we could be doing that via a Lambda function. And again, that Lambda function here that we can see is configured for that auto-scaling group to change to 2. And that's how we do a warm site standby in just a couple seconds. Back to you, Robbie.
So as you can see, you have a ton of flexibility when you're deploying a DR scenario in AWS. We've seen many different organizations that take advantage of multiple different DR architectures to suit different workloads because they have that flexibility in the AWS cloud. To dive deeper into these solutions, I'd encourage you to go to aws.amazon.com/disaster-recovery, where you'll find a number of different white papers, analyst reports, case studies, and other assets that might be helpful to you as you plan a DR scenario in the cloud. We also have some architecture resources at aws.amazon.com/architecture to provide you with further technical detail. And now we'll take a few questions from the Q&A window.